In this video, I want to help deepen your understanding of GD&T true position tolerance by reviewing deviation calculations, the concept of bonus tolerance, and showing you how to write a spreadsheet to determine if a part is within specification. Here is a drawing we will use as an example. You will notice that the part contains a hole, which has a size tolerance associated with it. The size tolerance requires that the hole be no smaller than 7.8 millimeters and no larger than 8.2 millimeters. The drawing also calls out a position tolerance associated with the hole. The position tolerance references three datums for establishing a datum reference frame for manufacturing and measuring the location of the hole. Datum A is the primary datum, which is this surface here. Referencing this datum implies that the axis of the hole must be perpendicular within a specified tolerance. It also references datum B, which is this surface, and datum C, which is this surface. These datums establish this corner as the origin for locating the hole. This is a basic dimension, which specifies the theoretical exact x-coordinate of the hole, and this is a basic dimension, which specifies the theoretical exact y-coordinate of the hole. This is the tolerance value, and notice that a diameter symbol has been included indicating that the center axis of the hole should fall within this cylindrical tolerance zone, which is 0.4 millimeters in diameter. Let's zoom in on the hole so we can better understand what this means. Here's the basic dimension establishing the true x-coordinate of the hole at 30 millimeters, and the basic dimension establishing the true y-coordinate of the hole at 10 millimeters. Here is the cylindrical tolerance zone that the center axis of the hole must fall within. Let's suppose the center of the hole was actually located here, shown by this green dot. Would this be within specification? Yes, it's easy to see that this location lies within the blue cylindrical tolerance zone. However, how would you know if the hole was within specification if all we had were the x and y coordinates given us from a CMM? In this case, the actual x-coordinate is 30.15 millimeters, which is a 0.15 millimeter deviation from the exact x location. The actual y-coordinate is 10.1 millimeters, which is a 0.1 millimeter deviation from the exact y location. We can calculate this distance, indicating how far the point is from the perfect location, by drawing this triangle. The base of the triangle is 0.15 millimeters, and the height is 0.1 millimeters. We can use the Pythagorean theorem to calculate the length of the hypotenuse, the square root of the base squared plus the height squared. This calculates to be 0.18 millimeters, which is the radial deviation of the actual hole from its perfect position. However, you should remember that the position tolerance of 0.4 millimeters is the diameter of the tolerance zone, not the radius, which means that we need to convert our radial deviation into a diameter as well by simply doubling the radial deviation of 0.18 millimeters to get a diametral deviation of 0.36 millimeters. If we compare the 0.36 deviation to our position tolerance of 0.4, we can see that we are within specification, since the actual deviation is less than the allowed tolerance. If, however, the center of the hole was located here at this red dot, the deviation would be 0.45 millimeters. If we compared that to the allowable position tolerance of 0.4 millimeters, we would realize that this red position was out of specification since the deviation from the perfect position was larger than the allowable position tolerance. Now that we know how to calculate the deviation and how to compare it to the position tolerance, let's talk about the concept of bonus tolerance. To demonstrate this concept, consider the red plate with a hole in it that will be assembled onto the gray part which contains a pin. The part will only assemble correctly when the pin can fit into the hole. If we look at the assembly from the top, we can see that the hole is larger than the pin, so that it will assemble easily. If the hole were out of the ideal position like this, the parts would still fit together. If the hole were out of position in the other direction, the parts would still fit together. But if the hole was too far away, the parts would no longer fit together. What if the hole was larger? Then it could be further away from its ideal position and still fit in the assembly. It could be out of position in any direction and still fit in the assembly. The concept of bonus tolerance refers to the fact that as the hole gets larger, it can be further out of position and still fit in the assembly, meaning the allowable position tolerance increases as the hole size increases. Here's the drawing of the machine bracket with a hole in it. Notice that the size of the hole is 8 plus or minus 0.2 millimeters. You will also notice that this drawing contains a position tolerance, which includes an MMC modifier, meaning that the 0.4 millimeter position tolerance zone applies at maximum material condition. Maximum material condition occurs when the hole is as small as possible. Therefore, if the hole was larger, then there would be more clearance with its mating part, allowing the hole to be further away from its perfect position and still fit in the assembly. In other words, if the hole is larger than MMC, we get a bonus tolerance equal to the amount of oversize. Here's a table where I will show you some examples. Since the size of the hole is 8 plus or minus 0.2 millimeters, a 7.8 millimeter diameter hole would be the smallest possible hole size, which would represent the maximum material condition. There would be zero bonus tolerance at this condition, and the allowable position tolerance would simply be that called out on the drawing, 0.4 millimeters. Now suppose that the actual hole size is 8 millimeters, which is 0.2 millimeters larger than the MMC hole size. In this case, we would be able to take advantage of 0.2 millimeters of bonus tolerance, since the hole is now larger and can accommodate being further away from the perfect location. This means that our allowable position tolerance is now 0.6 millimeters rather than the 0.4 called out on the drawing. Now let's suppose that the actual hole size is 8.2 millimeters, which is the largest acceptable hole size and is the least material condition. This is 0.4 larger than the MMC condition and would therefore provide 0.4 of bonus tolerance, resulting in an allowable position tolerance of 0.8 millimeters. To help you better understand these principles, let's write a spreadsheet to calculate bonus tolerance, allowable position tolerance, actual deviation from a perfect position, and determine if a part is within specification. I've created a new sheet in Microsoft Excel, and you'll notice that I've placed some headings. This blue area is for the drawing specifications, a minimum hole size, which is the MMC condition, the maximum hole size, which is the LMC condition, and the true x-coordinate and y-coordinate, as well as the position tolerance called out on the drawing. In this area over here is where we're going to put the actual measurements that could be obtained from a CMM, the actual hole size, and we'll calculate the bonus tolerance, as well as calculate the total position tolerance based on this bonus tolerance. And we can type in the actual x-coordinate and actual y-coordinate provided from the CMM, and then calculate deviation from the true position and determine whether or not the part is within specification. So let's go ahead. In this cell right here, the minimum hole size can be determined from the drawing, which equals the 8 millimeters subtracted the 0.2 millimeter size tolerance. The maximum hole size is equal to the 8 millimeters plus the 0.2 millimeter size tolerance. The true x-coordinate is this basic dimension here of 30 millimeters, and the true y-coordinate is this dimension here of 10 millimeters. The position tolerance is this diameter tolerance zone of 0.4. Let's suppose that the actual hole size is 8 millimeters. We can now calculate the bonus tolerance based on how far the actual hole size has deviated from the maximum material condition. So this cell would be equal to the actual hole size subtract the MMC hole size. So in this case we have 0.2 millimeters of bonus tolerance. So the total position tolerance would be equal to the position tolerance called out on the drawing plus the bonus tolerance, which is 0.6 millimeters of total position tolerance. The actual x-coordinate would be measured by a CMM. Let's suppose that that actual x-coordinate is 30.15 millimeters, and the actual y-coordinate is 10.1 millimeters. We can now calculate the deviation of the actual position of the hole from the true position. We do that by equaling the square root of the actual x-coordinate, subtract the true position, squared, plus the actual y-coordinate minus the true position, squared, close parentheses. Now you'll remember that this 0.18 millimeters is only the radial deviation. So let's go back into this equation and 2 times that so that we have a diametral deviation. Now we have the 0.36 millimeters. Now to check whether this part is within specification or not only will we need to check to see if the actual hole size is between these two values, but we will also need to check to see if this deviation is less than the total allowable position tolerance. And we will do that using an if statement. I'll type in equals and use an if statement. And the if statement first requires a logical test. And in this case, we're going to need 3 logical tests. So I will use an AND function, which will allow me to create 3 logical tests. The first logical test will check the actual hole size to make sure it is greater than or equal to the smallest possible hole. I will also check the actual hole size to make sure it is less than or equal to the largest possible hole. And I will also check to make sure that the deviation that we've calculated is less than or equal to the allowable position tolerance. That included the bonus tolerance. I'll close that parenthesis and then type a comma, which will now allow me to specify what value should be placed within this cell if all three of those tests are true. And I will type in the word yes, and I'll have to put quotations around it, indicating that it is text. And then I'll type a comma and now indicate that if any of those logical tests are not true, then the part must not be within spec. And I will type the word no within quotations again, since that is text, and then I'll close the parentheses. So this now indicates that the part is within specification because the actual hole size is between the smallest and largest possible holes, and the deviation is less than the position tolerance, including the bonus tolerance. Now that I have this spreadsheet created, I can highlight this row and just copy it down multiple times. Now I can keep track of many different measurements to see if the part is within spec. For instance, I could say, what if the part was 8.0 and the actual x-coordinate was 29.8 and the actual y-coordinate was 9.9. I could see that the deviation was 0.45 and that I would have a 0.6 allowable tolerance and that that would be within spec. I would encourage you to create a spreadsheet like this of your own. It will certainly make your assignment in this unit easier and may even turn out to be a good tool that you use in your career.